Hi, I'm Ryan Baker, and this is Big Data in Education. In this video, we'll be talking about Explainable AI, or XAI. Explainable AI is AI where the reasons for a specific prediction can be explained to a human. Interpretable AI, a related construct, is AI where the process leading to predictions can be understood by a human. Similar to Explainable AI, not quite the same. So let me give an example of explainable versus interpretable. Explainable. I think Ryan will drop out of high school because he has a low GPA and keeps getting into fights. Interpretable. The model says that zero point 0.1 lower GPA results in 3% higher chance of high school dropout, and the model says that each disciplinary incident for fighting results in a 6% higher chance of high school dropout. Another example. Explainable. I think Maria will get a correct answer on the next problem because she's gotten 3 of the last 4 correct on problems involving the same mathematical skill. Interpretable. Each correct answer increases the correctness probability 10% at first, and then that benefit goes down over time, whereas each wrong answer decreases the correctness probability by 3%. Explainable and interpretable AI are different challenges. They're both important. They have different affordances. With explainability, you can use any algorithm you want as long as you can explain a specific prediction afterwards. By contrast, some algorithms produce models that just aren't interpretable, even to experts. Now be cautious when you're reading papers or looking at work on this because although these are the standard definitions in AI more broadly, the terms are fairly haphazardly or interchangeably used in the EDM and LA communities. And a lot of papers use explainable to refer to both of these. Now what makes a model interpretable? Lewin Katinger, and note they call it explanatory, although to be fair, this paper is from before the terms became standardized. In order to have a model be interpretable, you need to be able to understand how the model works. You need to understand why the model is better than simpler alternatives, and understanding of this why should either advance our understanding of how learners learn the relevant material, or have clear implications for instructional improvement, or both. In this account, interpretability is facilitated by interpretable and meaningful predictors, and it's also facilitated by designing predictors based on theory. And finally, it's facilitated by predicting a variable that's well-defined and easy to understand itself. Interpretable models in this account, and I think it's true, tend to be relatively parsimonious. It's hard to really interpret a model with 375 predictors combined in 10,798 ways. If we compare these to uninterpretable models, those are models where we can't understand how the model works, we can't explain why the model is better than a simpler alternative, and the model doesn't advance our understanding of how learners learn the relevant material, or have clear implications for instructional experiences. It just predicts better. And sometimes that's good enough, but not if we want to be able to interpret or explain the model. An interpretable model is relatedly less likely to have interpretable and meaningful predictors. It could be combining interpretable and meaningful predictors in uninterpretable ways though. So you can have a model that's uninterpretable either because you can't interpret the features, the predictors, or you can have a model that's uninterpretable because even though you could understand them individually, they're combined in such a complex way that a human being can't understand them. It's also relatively more likely that an uninterpretable model is predicting a variable that's itself hard to interpret. And sometimes this also comes down to a variable that seems easy to interpret, not being quite as easy to interpret as we think of it. And for example, that might be suspensions from school. A lot of times we think about something like suspensions from school, well, you do something really bad, you get suspended. But also, as a lot of the literature has shown, kids get suspended for all kinds of reasons other than simply doing something bad, and some kids who do the same actions don't get suspended. So how can we tell if a predictor variable, is interpretable and meaningful? One of the things that people do, I like to call just so stories. And that's a case where we ask, can we tell a plausible narrative story about how a predictor would influence or correlate to the variable being predicted? If we can tell that plausible narrative, that just so story, this is just how it's so, then we can consider that the predictor is relatively interpretable and meaningful. If we can't tell such a story, how do we really interpret it? Now, Lewin Katinger talked about relatively interpretable models, but what if you have a model that's just not interpretable? Increasingly, people have said, okay, Contemporary AI models are really inscrutable. And can we try to explain those models even though the models themselves are hard to interpret? So this is explainability versus interpretability. We're not trying to interpret the model, we're trying to explain why the model made a specific prediction in a specific case, which might be easier. And there's a lot of methods for explainable AI. One of the big categories, the contribution the predictor makes to the model. So an example of this would be, how much worse does the model do if it doesn't have access to this predictor? So we build a model that has the predictor, we build a model with everything else except that predictor, we compare the two. Another way of looking at the contribution of the predictor is to look at what proportion of models within an ensemble, a set of models working together, contain the predictor. Random forest was the first AI algorithm to really be broadly used for explainable AI, and it remains one of the most popular because random forest already creates a large ensemble of models. And now what we do to explain the contribution of predictor is say how many of those models actually use the predictor. Another method along these lines is to take the average of the predictor's contribution to the final prediction in all possible scenarios. And this is SHAP values, which is one of the more widely used explainable AI techniques after random forest. No, I would say the most widely used after random forest. Another large category of methods for explainable AI is sensitivity analysis. For example, we might try changing each of the predictors and see which of the predictor changes most impact the prediction. That's LIME, another popular explainable AI methods. We might look into which predictor variables absolutely can't change or it's going to change the prediction, kind of the converse to LIME called CEM. Or we might ask, what are the smallest changes to the predictors that can change the prediction? And that's DICE. Another category, which is specific to neural networks, a very common approach these days, is layer-wise relevance propagation. In layer-wise relevance propagation, we take the result and we run the neural network that produced it backwards and look at which specific predictors or values have to stay the same as in the original data. So that's similar to looking at which changes are necessary to change the result, but we're actually running it backwards from the results and saying, what if we run backwards ends up still being the same? So as these few slides have shown, there's a lot of methods for explainable AI, and the methods are getting more and more advanced. But there's a problem, and as Vinitra Swamy and her colleagues showed, and the problem is that all of these advanced techniques for explaining a prediction often don't produce the same answer. So if you try DICE and SHAP and LIME, you might not get the same answer. And in their paper, they found that LIME, in fact, was the most outlier of the metrics studied. But if LIME is answering the question you want to answer, then it's the right choice. It matters, it turns out, which explainability metrics you choose. So it's necessary to think about what you really want to know. You can't just kind of like use explainable AI itself as a magic box that tells you what matters. You have to actually think about how you want to think about what matters. So to sum up, explainability and interpretability are important in a lot of cases if we want to understand what our models are doing and why they're making the decisions they make. But it's not exactly trivial, it's fairly complicated. And it really requires thought. Now after looking at all these, you might be saying, what about interaction effects? Well, as it turns out, canonical XAI methods don't really pay attention to this, but there are extensions for SHAP and specific as the most widely studied XAI method, including tree SHAP, and also non-tree SHAP with Shapley-Taylor interaction indexes. And also, as a quick note, if you input interaction terms to LIME as potential features, it'll incorporate them into the linear model it creates. So you can kind of hack interaction effects out of LIME. And that ends week 1. Next week, we're going to talk about another case where you really have to think about what you most care about, and that's diagnostic metrics. Are your models actually any good? Oftentimes, diagnostic metrics will disagree, and you have to really think about what you want out of your model. Thank you for joining me for week 1. I hope to see you in week 2. I'm Ryan Baker, and this is Big Data in Education.